Hello, everyone, welcome back to the channel Global Times USA. Please subscribe and like my videos. Today, we are diving deep into a major development. Ukraine launches 93 deadly drone attacks, Russia in shock. We'll walk through all the facets, the external view, internal systems to the extent known, performance, safety/counter, defense, the unique selling points, so to speak, for these weapon systems, cost/price or resource burden, and wrap up with conclusions and implications. Let's begin. When you look from the outside, what you see is a coordinated swarm of unmanned aerial vehicles, UAVs, many of them kamikaze-style or attack drones, launched simultaneously to strike multiple targets across Russian-held territory. The exterior of these drones is relatively simple and utilitarian. Lightweight composite materials, aerodynamic frames, low observable surfaces, minimal protrusions, often matte paint or camouflage blending with the sky. Their wingspans tend to be modest, sometimes quadcopter or multicopter forms, sometimes fixed wing, depending on mission profile. You may see small propellers, modest fuselage tubes for fuel or payload, sensor pods, and perhaps guidance antennas. Because they are designed for single use or limited reuse, the manufacturing prioritizes cost efficiency, compactness, stealth, or low radar cross-section over luxury or durability. Externally, many of these drones utilize modular payload bays, where explosive warheads or small munitions are mounted. Some have pop-out control surfaces or folding arms, especially in quadcopter or multi-rotor designs, to reduce size during transport and increase agility in flight. You might see small stabilizers, fins, or rudders to help stabilization and directional control. On the outside, you won't see large radar reflectors, large antennas, or extraneous structures. These are minimized to reduce detection. Some models likely carry optical or infrared sensors on the front, protected by small domes or transparent windows used for terminal guidance. The external design is a trade-off, enough structure to house flight systems, payload, and guidance, but as lean and stealthy as possible. In a swarm of 93 simultaneous drones, the exterior visuals would be striking. Dozens of small flying craft streaking across the skyline, weaving, taking different trajectories, sometimes with contrails, sometimes nearly invisible until the terminal phase. The visual impact of that many in motion is intended to overwhelm air defenses, saturate detection zones, force multiple fire decisions, and exploit gaps in radar coverage. The exterior also includes basic aerodynamic features, wings, rotor blades, control surfaces, and often a minimalistic small tail in fixed wing variants or nothing in multicopter designs. Some may include ballistic casings or shrouded rotor housings to reduce noise or turbulence. The exterior is quite Spartan, but every contour and edge is engineered for purpose. Turning now to the interior, and this is where complexity is higher and where much of the magic happens behind the scenes. Inside each drone, there is a flight control system, guidance and navigation electronics, power management, propulsion controls, payload control, triggering of the warhead, sensor packages, communication or data link modules, possibly stealth or counter, jamming subsystems, and structural support. For all this, the Flight Control Unit (FCU) is the brain. It integrates inertial measurement units, IMUs, gyros, accelerometers, GPS/GLONASS or alternative navigation systems, and executes path planning, stabilization, obstacle avoidance, and terminal targeting. The guidance algorithms might include preloaded waypoints, mid-course corrections, target reacquisition using visual or infrared sensors, and final homing logic. Power is supplied by batteries or small hybrid systems. Interior circuitry handles voltage regulation, power distribution, safety cutouts, and energy management to optimize endurance. Wiring harnesses are kept minimal, often with shielded cables to reduce electromagnetic interference, and connectors are rugged but lightweight. Payload interface is critical. Inside, you'll find a triggering circuit, safety interlocks, sometimes fusing logic, and detonation or explosive charge compartments isolated with insulation or shock absorbers. Sensors inside include optical/IR cameras, LiDAR or laser rangefinders, perhaps radar or millimeter wave sensors in more advanced models. These help detect the target, refine trajectory, and adjust in real time for moving or partially obscured targets. Some drones may include electronic warfare modules or jamming transmitters/receivers to confuse enemy radar or communications. Others may include decoys or chaff dispensers, though that is rarer in small drones. Internal structural supports, such as carbon fiber ribs or composite frames, provide stiffness while minimizing weight. The interior layout is tight. Components are densely packed but arranged to avoid interference and to maintain center of gravity balance. In many systems, redundancy is built in dual sensors or parallel circuits, so that a single failure doesn't doom the mission. EMI shielding and grounding are critical to prevent self-interference. Thermal management is also an interior concern. Heat from electronics or batteries must be dissipated, often via conduction to external body panels or small vents, though vents are minimized to reduce radar signature. Communication and data link modules are inside as well. Antennas often retractable or conformal, transmitters, receivers, error correction systems, encryption modules, and protocols to coordinate swarm behavior or respond to commands. These modules allow the drones to receive updates, share sensor data or positioning, or adjust in flight. Additionally, there may be onboard logic to detect defenses radar, jamming and reroute or abort, or to self-destructive capture is imminent. That self-destruct logic is part of the interior. Explosive charges or mechanisms that disable the drone in controlled fashion. In some advanced designs, the interior may also include small obstacle detection sensors, ultrasonic, infrared for low-altitude flight near terrain or in cluttered areas. In swarm operations, interior firmware includes swarm coordination logic, algorithms to maintain spacing, avoid collisions, choose which unit attacks which target, reassign targets if some fail, and redundancy fallback. The drones might also share target updates or sensor data mid-flight via mesh networking. Such swarm logic is often done in distributed fashion, no single central controller but collaborative autonomy. Because these drones are often expendable or semi-expendable, interior components emphasize cost-effective but capable electronics rather than premium long-life parts, but balance is needed. A failure mid-flight means mission failure, so reliability is still essential. Components often are hardened to handle shock, vibration, electromagnetic interference, and even minor counter-measures, so the interior is where all the planning, sensing, decision-making, execution, and self-protection happen. External simplicity belies a highly integrated internal architecture tailored to precision strike, resilience in contested environments, and effective coordination. It is in that hidden internal space that the sophistication of modern drone warfare reveals itself. Performance is the next dimension. In this assault of 93 drone attacks, performance is measured by range, speed, endurance, payload, accuracy, maneuverability, resilience, and saturation capacity. Range: many of these drones can traverse tens to perhaps a few hundred kilometers depending on power source, fuel or battery capacity, efficiency, and aerodynamic design. In these attacks, some likely started from launch bases relatively far behind the front lines, indicating respectable range. The performance in range is critical to strike deep targets and bypass front-line defenses. Speed: these drones likely vary in speed profiles. Cruise speeds may be moderate for fuel efficiency, perhaps 80-150 km/h in fixed-wing types, perhaps slower in rotor drones. In terminal dive or attack modes, they may accelerate to higher speeds or maneuver aggressively. The ability to evade interceptors or defenses depends on acceleration and maneuver margin. Endurance. For a mission of this scale, endurance is key. They must loiter or adjust trajectory mid-flight. Some may allow tens of minutes to perhaps over an hour of flight, depending on battery or fuel. Endurance also includes the ability to hover or slow down near target zones, search and strike. Payload. The warhead size is limited by weight constraints, so likely small to medium explosives or fragmentation charges, shaped charges, or a small high-explosive payload. The payload must balance with fuel/battery weight. Some drones may carry multiple submunitions or cluster payloads. Accuracy. Thanks to onboard sensors, mid-course correction, visual or infrared targeting, and guidance algorithms, the accuracy is high, capable of hitting hardened structures, airfields, command posts, radars, or vehicles. Precision is critical so as to maximize impact and minimize waste. Maneuverability. In a contested environment, drones must dodge countermeasures, adjust altitude, avoid detection, and sometimes perform evasive maneuvers mid-flight. Some may fly low-terrain masking, weave or adjust trajectories in response to radar, or change course to avoid defenses. Resilience. They must cope with jamming, electronic warfare, GPS denial, or radar tracking. Performance is partly judged by how many of the 93 reached their targets despite Russian air defense efforts. The saturation tactic, sending many drones at once, degrades the effectiveness of defenses, because air defenses can only intercept so many at once. Saturation capacity. By launching 93 simultaneously, Ukraine tests the performance envelope of coordinated saturation attacks. The idea is that even if many are intercepted or neutralized, enough will reach targets to inflict damage. Performance, then, is not just individual drone metrics but system-level throughput. Moreover, performance under varying weather, altitude, wind, and interference matters. These drones likely handle moderate wind, atmospheric variability, and operate in contested electromagnetic environments. The ability to maintain link, adjust in flight, and complete the mission under those constraints defines real-world performance. In the specific incident, the success rate, how many drones struck, how many were shot down, is an indicator of performance. Reports suggest Russia was caught off guard, indicating high performance in planning, timing, and execution. The speed at which these drones penetrated defenses, reached target zones, and struck critical infrastructure or military assets showcases robustness. The coordination among the 93 indicates the swarm command and control performance was credible.